Welcome to possibly the most thought-provoking chapter in the textbook. So, as the introduction points out, that up to now we've been, memorizing terms and labels and, um, you know, memorizing. But in this chapter, we're dealing with theories. And when I entered the field, Skinner was pretty much anti-theory, and as was Watson. And a lot of this stuff occurred during my graduate training and after I, did my postdoc and came back to Scranton to teach. So I overlapped with a lot of this stuff, but I was in grad school in a learning theory graduate program, although that wasn't my specialty. And a lot of this stuff happened after I left the building. Um, Theories can do more than simply than just simplify and organize. You can see that this author is a big fan of these theories, and he uses them to make. He and others have used them to make predictions, and then research has been done to test predictions. And okay, I agree. And the beginning theory, and we've seen Rescorla a few times, and there's Rescorla and Wagner. I know that Wagner died recently. I think Rescorla is dead too. Um, and if you look at the year on Rescorla and Wagner, 72, that's right at the beginning of my graduate training. So this was new stuff, uh, but I didn't care that much. But these are huge figures in the field of learning. And in terms of Wagner, two of your peers, two graduates of the University of Scranton, were teaching assistants for Wagner. And allegedly, he loved Scrantonians. He liked the way they worked and the way they thought. And he was a force to be reckoned with. And there's Kamen and the Kamen's blocking and unblocking effects. Um, Important stuff. And Rescorla and Wagner dealt with those things. So association strength on the y-axis here, it goes up to 1. In most examples, it caps at 1. It doesn't have to. It can go higher. But 1 is often used as the maximum for a growth curve that goes from 0 to 1, or you could almost think of it as 100%. And there's lambda. So that's the most you can learn in this situation. And if you look at the CS-US pairings in that figure, um, you can see that early learning, there are big jumps in the acquisition of response strength. So this is not; these aren't real data. This is theoretical data. But notice that in one jump you go up 0.2, and that's going to be an important number. And in the next jump you don't go up 0.2. You go less than 0.2, and then less than 0.2, and less and less and less. This is a bit like the example of the arrow going to the target, and with each unit of the time it gets halfway to the target. So the asymptote, lambda, the maximum, you might say you never get there. This relates to why professional musicians continue to practice, because they feel they can always increase their performance just a little bit. So lambda is going to be a very important concept in this chapter. And that is figure 401, right? Yes. So the book's discussions of all this are excellent, and I absolutely cannot walk you through the discussion that the author provides for everything in this chapter. There's just too much. And for me to talk, I would end up just reading the chapter. I'll deal with the major concepts, and then you have to, get a glass of water, make yourself comfortable, and focus on this stuff to learn what it means. So, Rescorla and Wagner, by the way, I may occasionally say Wagner. My German training kicks in, but Wagner. Associative strength, that's what's being graphed on the y-axis here, and it's V. And there it is in a formula. And before the V is a delta symbol. And, delta is a pretty universal math symbol for change. So delta V is equal to alpha beta times the quantity lambda minus V, close parentheses. So the change in V is alpha beta times lambda, which is often 1. It doesn't have to be, minus response strength prior to that training trial. Now, response strength starts at 0, and lambda is 1. So if you take that down here, lambda 1 minus the beginning of response strength 0, 1 minus 0 is 1. So delta V in this first trial is going to be alpha beta times 1, because 1 minus 0 is 1. The book deals particularly with alpha. These are the salience relevance of the CS and US. For simplicity, I usually just think of alpha beta as one value, kappa, which is a constant for each learning trial. And by the way, if we look at the constant alpha beta for this trial up here, if lambda minus if lambda minus V on trial 1 is 1, and you multiply that by the unknown kappa, and you get between trial 1 and trial 2 a delta V of 0.2, and by now some of you are probably pounding your heads into the table. I'm sorry. The book does an excellent job here, and I'm just trying to help. But you can now figure out what kappa is, or alpha beta, because 1 times the unknown is 0.2. That kind of tells you that the unknown is 0.2. So in this formula, delta V between trial 0 and 1 is 0.2, equals 0.2 times 1 minus 0, or 0.2 times 1. And by the way, I'm going to make you do some of this math. So don't let your eyes glaze over and not try to work out examples with these formulas, because your author does it, and it's meaningful. You can, I remember lecturing about this many times, and some people really got it when they saw why alpha beta, or my kappa, is 0.2, because an unknown times 1, that value is the unknown, 0.2. And then it gets smaller and smaller, because on trial 2, you go into trial 2 with a V of 0.2. So let's just look at that for a second. So on trial 2, delta V for trial 2 equals the constant, which is 0.2, times lambda, which is a constant for this example of 1 minus 0.2. Now 1 minus 0.2, because V is what you went into the trial with, 1 minus 0.2 is 0.8. So if you multiply 0.8 times 0.2, you get a delta V of 0.16. And the sum of 0.2 plus 0.16 is 0.36, and so on into the night. So you may have to do some of this math. Lambdas don't have to be 1. They're often 1. Kappas certainly don't have to be 0.2. They may be. And you have to, years I've been teaching this material, some of you are going to have trouble differentiating between delta V and V. And this formula is for delta V. And delta means change. It means change in V. And V is the response strength that you went into the trial with. So there is a V in the formula. And on trial 1, V is 0. And on trial 2, it's 0.2. And on trial 3, it's 0.36, and so on. So as you subtract V from lambda, you get smaller and smaller numbers, which means your delta V is smaller and smaller. Please, please, please spend some time doing some simple math for this. At some point you may need a calculator because the numbers are going to get weird. But so far we haven't needed the calculator. We can do it in our head. And trust me, you may have to do this for the quiz. Rescorla-Wagner is huge. And so there's a discussion. Delta V is change and alpha is change. Alpha and beta are fractions. They each have values between 0 and 1. How salient is the CS and US? CS for alpha and US for beta. And again, I tend to just treat them as one number. And what's this about? In terms of everyday conversation, it's how surprising was the training trial. And the more surprise you have, the more delta V you have. And if you expect nothing and you get a 1, that's a pretty big surprise. If you expect 0.2 and get a 1, that's a pretty big surprise. But the amount of surprise you get decreases across trials, and you can do the math for this. This is pretty magical. So then, there's prediction errors, and it gets smaller and smaller. And conditioning thus works in a sense to correct the prediction error. So let's look down here. So they have two examples. So associative strength, V, they have two examples, one where the dashed line is at 1, which is what we did in the last page. And in the second one, the dashed line is at 2 to show that you can have different lambdas. If you can handle 1, you can handle other numbers. Just make sure to mess with it when you have to. And then on the right, so we have blue and red curves, and on the right we have blue and red curves. On the left, the blue and red curves are going to the respective lambdas, and on the right they're going to a unitary lambda of 1, which is conceptually maximum. And you can see the effect of different alphas, or I would say kappas. So the blue kappa is pretty darn big, And just look at that for a second. So look at where that dot is. And you should be able to, if you're following this lecture, and I certainly respect that this can be difficult to follow. I've taught this many times, and people can struggle. But if you don't master these concepts here, uh, you're I'm not going to let you go. So what's the alpha beta, or for this book, alpha for me, kappa for the blue line? What is it? Look where that dot is. What value does it have? Just like on the preceding page, it goes from 0 to 0.5. So I betcha that the salience of the CS, the alpha, is 0.5. And the red line goes up to 0.2, which we've already dealt with. So if you spend some time with this, you'll get comfortable, and the cold sweats should go away. And if you have a study buddy, have them make up little examples for you and work out the math, because I swear I will have you make up some of the math. And please pay attention to the difference between delta V and V. For some reason, the letter V is so salient to students, they don't see the delta. And sometimes I'll ask you about delta V, and sometimes I'll ask you about V. They are related, but they are not the same. And here we've added the sum symbol. So on trial 1, V was 0. On trial 2, 0 plus 0.2 is 0.2. And then it's, U delta V 0.16. So the sum of 0 plus 0.2 plus 0.16 is 0.36. So, V, not delta V, V accumulates by the sum of the V's. Take a break, look at that, think about it. You'll see the wisdom of it. And this was pretty darn brilliant. 72, I didn't care too much about it, but it's pretty brilliant. I was doing neuroscience in 72, but still I was exposed to some of this. And here's my good friend Cayman. Cayman uses a CS where the lambda is equal to 1, which is a nice example. At the end of the first phase, the rat has thus learned that the associative strength of the noise, because they become fully cognizant that noise predicts the unconditioned stimulus. So the sum of the V's for noise is 1. They've learned all they can. And now during the second phase, but now you add light to noise, and you go back and review this ln plus noise. So let's look at what's going to happen here. And I'm going to spend a lot of time on the beginning of this chapter and the middle half to the end of this chapter. You are going to have to slog through that on your own. It's all very important, but this really can be mastered, and I'd like you to master it. So here's something to think about: delta VL. So change in response strength to L, delta VL equals alpha beta, which for me is constant, equals lambda minus the sum of V. So sum of V will be again, the total associative strength. So delta VL equals alpha beta, lambda minus the response strength to noise plus the response strength to light. Now remember, the response strength to noise was 1. And in other words, it's the maximum for this example, 1. So what kind of delta VL are you going to get if you subtract, if lambda is 1 and you're already at 1 with Vn, then 1 minus 1 plus 0, because you've just begun trials with light. So 1 minus 1 plus 1 is 0. And 0 times any alpha beta is 0. So the change in value of light is 0. So here, my beloved Kalman blocking effect, you have a formula for it. You've already learned lambda for noise. We give you a noise plus light training trial. You're already chill with the noise. You're at lambda. 1 minus 1 is 0. 0 times anything is 0. And delta V for the light is 0. Brilliant. And here this is with real examples, or more real numbers. Delta V for the light is 0.2. We haven't changed that. Lambda is 1. 1 minus 1 plus 0. 1 minus 1 is 0. 0 times 0.2 is 0. Delta V is 0. Brilliant. Of course, this assumes that you've conditioned the noise to maximum. Now, you could change the lambda if you wanted to, and that would cause changes in light. But let these numbers wash through here. So here we've changed lambda to 2, and you've already learned 1. So 2 minus the quantity 1 plus 0. So 2 minus 1 is 1, and 1 times 0.2 is 0.2, and delta V for light is 0.2. So if you increase the value of the unconditioned stimulus, you can get learning to the light. You got to play with these numbers, and this is really cute. Extinction. So the model provides a ready account for extinction, and of course, in extinction, you don't. It's Bell without meat powder. It's light without shock. It's noise without shock. V is 0. So let's see how that goes. So delta V for the noise stimulus equals 0.2, because alpha beta is going to stay the same. But now you have no unconditioned stimulus. So the lambda inside the parenthesis has gone to 0. And 0 minus 1 is minus 1. And minus 1 times 0.2 is negative 0.2. So delta V for noise is negative 0.2. I mean, this, if you're getting this, you have to be impressed with how well it works. So there's an example of conditioning with the 0.2 and extinction with a 0.2. The you never get to typically to get to fully to the lambda of 1 value. So this animal only goes up to about 0.9 something. So the difference between the first and second trial and extinction is not literally 0.2, but it's ballpark. And then across extinction, where the animal is exposed to no US, no US, no US, lambda equals 0, 0, 0. the negative numbers get smaller and smaller because the animal's expectations become more realistic for extinction, and you get that function. Um, Pretty slick. Um, okay. Um, so here we have condition inhibition. This is getting trickier, but it should make sense. So obviously we're not using a alpha beta of 0.2 here. That's not important. It's more like 0.3. And in phase one, light in the US, and you get the normal learning function. But in phase two, you don't simply have light, no US, you have light noise, no US. So the animal expects one, but gets nothing, which creates a negative number. And that negative number is applied to both the associative strength of the light and the noise. And oh my, look at the purple line, which is nice. That's clever because it's a combination of red and blue. So you don't expect anything the first time you've seen the noise. But on the second trial, you're at negative 0.2. So here they're assuming that you have gotten to maximum lambda. And so you have a big drop in the associative strength of noise, but interestingly enough, a smaller drop in the associative value of the light. And then what's the red light, the red line? That's the sum of all your brain parts. In this case, there's only two brain parts contributing to this behavior, the associative strength of light and noise. But when you add the positive VL to the negative VN, you get what the animal actually does. So from the outside of the animal, all you see is the red line. But theoretically, what's going on in the animal is the associative strength of the light is going down gently, and the negative associative strength of the noise is going down fairly dramatically. And work on that. Please work on this until you can understand it. The chapter will be so much easier. So talk, protection from extinction and clinicians. Again, classical conditioning is vital to much of effective clinical psychology and addiction and love, and that discussion of protection from extinction is important. Um, so these are more data. This is cute. I've substituted the V values of the light and buzzer for V. So we're looking at the change in delta V for light, and we're keeping the alpha beta my constant at 0.2. But you have combined two stimuli, each of which has a lambda of 1. So for VL, you expect 1, and VB, you expect 1, and 1 minus 1, or plus 1, is 2, and 0 minus 2 is negative 2. So even though there's more training here, this is not extinction. Negative 2 times 0.2 is negative 0.4. Yipes. So you're predicting a reduction in the associated strength of light because of more training, because the animal expected more of a stimulus than it got. It expected a 2 and it got a 1. This was magic back in the day. And then there's discussions of all these new predictions, and he goes through examples. And you have to be able to discuss these training trials. And so light shock, noise shock, light shock, noise shock. But in phase 2, light noise shock versus the other group, which is light noise and a new stimulus shock. And then you're asking during testing, what's your associated strength for light and noise, and the stimulus, the new stimulus X. And if you stay calm and you look at these data, they should make sense to you. So this is phase 2, where the associated strength of the light is going down, but in terms of the animal's behavior, if there were and the purple line is down there, down below, the noise is subtracting from the light associated strength. And then in the other condition, you have delta V, which is what the animal is doing. You have the values of the light and the noise, which are in synchrony going down because they were both associated. And then the value of X, the new value, is going below 0. Lots of there's over expectation. You expect more than you get. And again, the numbers should make sense to you. Delta value n 0.2 times 1 minus the quantity, 1 plus 1, and 1 minus 2 is negative 2, and you multiply that by 0.2, or 1 times 0.2, negative 1 times 0.2, and you get negative 0.2. So keep pounding on this stuff. The over expectation effect is very impressive that this stuff works. It's really quite incredible. So decreasing associated strength because of additional training, really pretty amazing. So you can see, I mean, he was a learning guy as this stuff came out. I can just imagine how excited the field became when they could look at these theories and make predictions and then design experiments and test the theory and prove them right. And now context is coming up in this, and I'm not going to say very much about it, but you're in a context, time in a context. It has multiple features, and later in this chapter, we're going to start talking about nodes, and that will start blending us into cognitive psychology, which was B.F. Skinner really hated that, and there was a huge battle between cognitive and straight behaviorism, Skinnerianism, and cognitive one, which is reflected in this chapter. Okay, so we've seen these figures before. So on the top, you have negative contingency. The blue dots are never associated with the CS. But in the second one, there's zero contingency, which means it can be associated, but the blue dot is not predictive. And there's a discussion of these two types of stimulus presentation, and there's a discussion of a theory promoted in part by Ralph Miller, whose picture is coming up here on the bottom, comparator theories, which are not perfect. They can explain some things, but not all things. Ralph Miller, I don't know if he's still on the faculty there, but he was the learning guy at State University of New York at Binghamton, and I knew people who were graduate students there, and I actually helped him design a pain test that he needed to use. He was intense, which I think tends to be the case for classical conditioners, and brilliant. He had a really good and productive lab. And here's some problems with Rescorla and Wagner, and there are discussions where it doesn't quite work, and they are important, which means something has to change, something has to improve. And here's an interesting theory for blocking by McIntosh, which focuses more on the alpha beta, really the alpha for the salience of the CS. And you got to watch these figures. So here we have noise shock for phase one, for phase two, light noise shock for group two, but not group one. And then in phase three, light noise with a very intense shock. And then we test for light. And we've been looking at V and delta V, and we have become used to things going up being stronger, but now we've gone back to suppression ratio because these are real data. And think about it. Take a second and think about it. Does the red group or the blue group show more learning? And here, the blue group is closer to 0.5. So there is less suppression, less learning. And the red group is pretty nailed. They are pretty darn suppressed. So every time you run into these figures, you have to figure out what's on the y-axis, or you're going to get in trouble. And there's attention and the McIntosh model and attention. And if you're not paying attention to something, you're not going to learn very much about it. And McIntosh was concerned with this, and he could do some interesting things with this theory that others couldn't, including it explained latent inhibition, which we saw can be trouble for the pure Rescorla Wagner. So, and then unfortunately, this author knows too much. He knows the literature, all of it. He doesn't give you the simple answer. He says, yes, there are some data that support the McIntosh model, but there are other data that don't. And what can you do? I mean, it's true. So what's on the y-axis here? Suppression ratio. And again, higher values indicate less suppression. And you have two groups, tone plus shock, light plus shock, and then tone plus shock. And you can see that group one has less suppression than does group two. So there's more learning in group two, more suppression. Hall Pierce, these guys look friendly. I'm always trying to evaluate what they look like. Hall and Pierce have an interesting theory, and Hall-Pierce negative transfer. The value of alpha changed during CS during phase 1. So take a look at that, and of course, if the value of alpha changes, what you're multiplying into lambda minus v, or actually the sum of v, that will change too. And they came up with a model, and I love it. The animal would not waste mental effort paying attention to a CS whose meaning it had already well understood. You can see cognitive is creeping in here, and it does help make good predictions. Notice here, the sum of v, don't forget that. And here's our friend the rat orienting towards a light. And there are 3 conditions where the stimulus is partially associated with the US or continuously associated or not. And this is not suppression ratio. This is orienting toward the light. So higher numbers are more. So partial, you're paying more attention. Continuous, you got it. You don't have to pay too much attention. And no association, no poking. Good stuff. And as is often the case with theories, if you combine theories, they can work better. And there's a discussion of efforts to bring together the 2 sides, hybrid attentional models. Good stuff. What does it all mean? Rescorla-Wagner was a game changer. It shook the earth, but it's not perfect. And other people have come up with theories that can explain things that Rescorla-Wagner can't. And what does it mean? It means we have more research to do and more thinking to do. And now short-term memory and learning. This model down here is important, and let's spend a few seconds looking at it. So a stimulus comes into sensory memory, sensory store, and the sensory store passes that information on to short-term memory. And I'm not in love with this term, self-generated priming. It does come from yourself. It comes from your own sensory systems, but I wish there were a slightly different term for this. So information can get your attention in short-term memory because of an external stimulus that you transfer into it. Of course, there's also long-term memory. And long-term memory, relatively long-term change in behavior potentiality based upon experience, that can send information into your short-term memory. Like I could ask you what your phone number is, and it would come popping out of long-term memory and into short-term memory. And you can pay attention to that, or you can pay attention to what's come in to your sensory stores. And that is better named retrieval generated priming. So that's I like that one. Self-generated priming, not in love with that, but that's what they call it. And there's discussion of long-term memory and Trivial Pursuit and priming, which can affect the salience of the CS, and also the surprise, if that's relevant. And you can also do the same thing for the unconditioned stimulus or unconditional stimulus. And this is research working with Wagner. And in '76, they were still doing the eye blink. And this is clever research. And Terry obviously is clever. I don't know where Terry ended up. But that's good research. Remember how compulsive you have to be to do rabbit eye blink, because they don't learn that response very quickly. Um, and priming and latent inhibition. So we're revisiting some of the things from the earlier chapters and trying to deal with them uh, with these variants on the modern theory. And there's Boughton, your author, and so here we have a Boughton piece of research that he did with some of his students with different kinds of priming, whether the stimulus is the same as the original stimulus or different. And you can see now what's going on here on the left. That y-axis is uh, food cup entries. So more is more, more is more learning. The control has the most learning. The different prime is a little bit worse, but it's still darn good. So the CS is very salient. But when you pre-expose to the same stimulus, the CS seems to be less effective, and you get less learning in that situation. And it discusses how priming can interfere with learning. And surprise comes up here again. Surprise will be important for a lot of the chapter. So here's habituation one. I'm sorry, habituation, which we've talked about before, and this is a cute um, study involved involving self-generated priming. But again, that means the stimulus is delivered to the animal, and on the y-axis, um, you have the amplitude of vasoconstriction. So more is more. And in the right column with S2, you can see that with a different stimulus, you get a lot more vasoconstriction. And on the bottom, you don't get much of an effect at all. So that's useful. Um, we've gotten to the point in the chapter where I can't add too much. Um, and here's a summary. It's philosophical. What does it all mean? And by the late 1970s, classical conditioning was being interpreted from an explicitly cognitive framework. And I threatened you with that. And clearly, your textbook author is of that perspective. I never crossed over, but I'm I'm trying to talk the talk. Due in large part to the Wagner model, it became conventional to speak of the role of short-term memory retrieval and rehearsal when discussing conditioning. So the Wagner remained a powerful force in this area. So now we're beginning to move into more cognitive machine learning type models of things, and the idea that I'm comfortable with the idea of the brain having multiple pieces that interconnect with other things. And cognitive psychology says the same thing. So you have shock nodes and light nodes and tone and noise and the context, which we're going to deal with a lot in the latter part of this chapter. So long-term memory is a place full of memory nodes that may be associated with one another. Uh, and associations are based on arrows. So the notice the tone shock is a solid line, and the light and context are learned, and they're dashed lines. Um, Wagner again, standard operating procedure, and the book points out that this is not a brilliant name for things, but people started using it, and it stuck. This is not mathy, but it's graphy, and he says when a CS or a US is presented, its node is first activated into an A1 state, and then that decays, and as it decays, an A2 state starts taking over. A1 is brief, A2 is longer, and then after A2 is over, you rest in inactive state. Um, and there are discussions of what things go into uh, SOP. One thing that's important is the CS can activate the US node only to the level of A2. That is the magnitude of A2. And more cognitive stuff, that nodes are made up of many things that are put together. And that only if both the CS and US are in A1 do you get learning. And there's a picture, I hope, yes, on the next page. So here's a graphic representation, mercifully no math. You have a stimulus, and that stimulus can be the CS or the US. And the stimulus strongly activates the A1 state. And as that is fading, but not gone, the A2 state grows. Notice the A1 state is like straight up the page. And the decay of the A1 stage, the red line, is pretty steep too. But the A2 stage almost looks like a learning function where it goes up fast, and then it slows down at its asymptote, and then it goes down slowly across time. So by the end of the, even by halfway through the A2 in this example, the A1 is gone. So you've got A1 and A2, and these are relevant to both the CS and the US. Wagner must have been brilliant. And we're talking about short-term learning and long-term memory, and nodes. And here is US soon after CS. Remember, back maybe 2 chapters ago, delay and trace conditioning. So here the CS and the US are delivered fairly close in time. Notice that the US A1 function comes up while the CS A1 function is still alive. And you need that for learning to occur. So the second, the US A1 in effect hits the decaying CS A1, you're going to get learning there. And the decaying functions are relevant too. And then here's with a long trace where you have your A1 and you let it decay to 0. Your A2 for the CS is still there, but because the US A1 function does not touch the CS A1 function, you're not going to get learning there. And here's backward conditioning, which, as we know, doesn't work too well. And once again, in this figure, you don't have an overlap between the A1 function for the CS and US. So you're not going to pick up associative strength there. Sorry, I'm standing up. Sorry, that was so obvious. And here's a discussion of those figures and what they mean for learning. So it's just, words, good words, well written, describing what's going on in that figure. And there we've added an X stimulus and how the SOP theory deals with that. So, that worked well, but Wagner being Wagner, he wasn't happy to leave it alone. So they expanded their model, and they're still using rabbits. And the ASOP, affective extension of SOP, admits that emotions are important and they have to be considered in this training condition. And they do a good job of dealing with that. And there's a figure where the CS has a sensory link to the eye blink, but the US can have a link to fear and a complete association or improvement of the SOP theory. You have to add the emotional affective response. And lots of words, well described. And backward conditioning. USs have multiple qualities, absolutely true. Traumatic events in their lives. This again is why classical conditioning is relevant to clinical psychology and dealing with fears and potentially phobias. And then more cognitive. Elemental versus configural CS nodes. Fancy words, but really, quite understandable and well described. And oh my God, Pavlov comes back from 1927. External inhibition, which we had trouble explaining before, but now with this discussion, we are able to deal with this. Intuitively, it occurs because the tested stimulus CSAB is different from the one that was associated with the US CSA. There is imperfect generalization from A to AB. Adding B to A thus causes generalization decrement. Pretty brilliant the way they have worked this out. And then we have Peirce's configural theory. So many theories. But I hope by this point in the chapter you can see that the theories stimulate research, valuable research, not useless research. And they can make non-intuitive predictions that bear out. So here's cognitive. So on the top, you have elemental, where you have three stimuli, ABC, being associated with the unconditioned stimulus. But then there's configural, where the gestalt, the group ABC, is collectively associated with the US. So that's an important distinction. And boy, that's cognitive. And those are nodes. And cognitive one. So we have positive patterning and negative patterning, and more with Peirce. But then Wagner was able to, defend some of his stuff, and you can see the theories are generating lots of research and discussions of middle C and E and E flat and getting kind of cognitive. this is quite a study. So stay calm and look at the y-axis. This is not condition suppression. It's mean percentage condition response. So on the left, you have the stimulus paired with the US is either A or ABC. And then we do 3 test stimuli. Having trained with A, we test with A, AB, and ABC, or having trained with ABC, we test with A, AB, and ABC. So when you condition with A, not surprisingly, you get maximum responding with A, and you throw in a B, and that weakens the response to the combination stimulus, and if you throw in the C, it weakens even more. But look at the flip side. So you've been trained with ABC, and we give you an A, and you're not feeling it. But we add the AB, and you're happier with that, and then we throw in the C, and you're happy as a clam. So that makes sense. Um, the what does it all mean again? Which means this is going to get thoughtful, and there's going to be competing data. Um, nowadays when people use SOP, they mean the original model. Uh, if you're dealing with effective responses, you usually add the term ASOP. Um, Kuhn. Uh, Kuhn is a big name in the history of science, what science is. Kuhn talked about paradigms um, in biology. Arguably, the paradigm of biology is evolution, and the in psychology we're a little ragged on more than a little ragged on paradigms, unless you assume that everything relates to evolution, and then we're not. But if you ever want to read something about the philosophy of science, Kuhn is good, and the SOP model paradigm, in which almost all contemporary research on Pavlovian conditioning can be described and understood. This is the bookend to the beginning of the chapter. So in the beginning of the chapter, the author was saying, we've been memorizing this, we've been memorizing that, we've been learning this term, we've been learning that term, but we haven't been trying to make sense of them, to put them in a sense into a paradigm. And SOP uh, comes darn close to doing that. So we have come to the end of this chapter. It is a beast. You can't deal with the chapter without some serious reading and reflection. Um, and early 70s, again, that's about when I started graduate program. And I like the Rescorla Wagner because I like the numbers. And it explains a lot of good stuff. But now we're talking much more about SOP and ASOP. The Rescorla Wagner had problems. Other people came along with theories to try to resolve those problems. And then Wagner just kept on chugging along. And the the two nodes being activated by CSs in US, and they both have to be in the A1 state or learning doesn't occur. And then cognitive nodes are cognitive, short-term memory, long-term memory are cognitive. Again, I don't like the term self-generated, but a stimulus triggers it, whereas long-term memory can be retrieval generated, which is good. Um, and then there's nodes, and I never met Wagner. I wish I did. I believe that's the last page. No, no, then there's Aesop. And although conditioning theories will continue to change and advance, SOP theory with extensions is a powerful theory that can account for many of the most important effects in classical conditioning. And by the way, it's not just classical, as we'll see. So the author is paying homage uh, to theories that changed the field he was committed to. Um, I can feel it. I believe it. I respect it. Good luck with this. Good luck with this. Uh, and that's the end of this story.